we are going to keep doing some chi-square problems because it doesn't make sense that in the world everything has the same likelihood of happening. So when your expected values are the same, what you're saying is that you've got the exact same likelihood of each one of those particular categories occurring. And that doesn't even make sense. It's much more likely that there's a difference in likelihoods of what's happening. So let me just make myself here that I'm taking some notes on chi-square, and I'm going to put two little pieces of information. This is going to be based on when I've got problems that I'm given percents in the problem, and that there's different expected values, so that we're not talking about equal likelihood. And these are no different and no more difficult. You just really have one more step. So when you're given percentages, so if they tell you there's a certain percent probability in the population that whatever that category will occur, you just have one more step that you have to go through until you can actually have your expected values. So what you do is you're going to use the total number of observations. So you see how what size your set is of the data that you observed, and you're going to use that total, and then you're going to multiply it by the percent, and that'll tell you what percent of what you observed that you would expect to be what that category is. So I've got some problems. It's interesting to me that we forget that AP Biology is a global. But it's a global program, so you've got people in Canada. So let's see here. That's a bit large. Could be a little bit smaller. Okay, that's good. I'll move my head out of the way. My head's always in the way. So the first problem is they're looking at the population in Canada, and they've gone through and done a census just like we do, and they know the percentage of the population, the whole population, based on different age groups. And they're wondering, they're going to test to see if this group of 455 people who live in Red Lake Village in the Northwest Territories, if they actually have that same percent distribution as well. So what we'll do, I'm going to write these down real quick. So we've got a category of less than 5, less than 5, 5 to 14, a huge group of 15 to 64, and then over 65, that's our age. And then you do not directly use the percentages. You can't. Chi-square uses actual numbers. So this is a percent of the population. I need numbers of people because that's what was observed here, and that's what we would use are actual numbers. So you do use the observed values. So there's 47, 75. And it makes sense that 288 would be large because that group has a huge bunch of people in it. And then I'm going to write my percentages down here. So I've got 7.2, 13.6, 67, and 12.1. And now I'll work with those numbers. Okay, so the first thing you're going to do, let's make a little list of things we're going to do. The first thing you're going to do is you're going to record your observed, because those are going to be an actual count. So you went out and you counted 47 little kids. So those are actual numbers. The second thing you want to do is you want to get the total of the observed, so you know how big your sample is. So if you add all these up, you know, it's funny. I bet, I don't even know, 6 calculators, graphing calculators, and I never had batteries, because people come in here, my students, and they're having a test in math and they don't have batteries, and so I give them mine. And then I end up with all these calculators that don't have batteries. So the first thing I'm going to do, I did record my observations. I'm going to get the total. I know they told me it was 455, but I'm going to add anyway. So 47 plus 75 plus 288 plus 45. And sure enough, there's 455. That number is extremely important, because you're going to base all of your expected values on this number. So the next thing you're going to do is you want to go, okay, I would expect that 7.2% of my total observed would be less than 5. So you're going to multiply your total observed by each percent, and that's going to give you your expected values. So 7.2%, you just have to remember that you're going to convert your percent to a decimal to multiply. The other thing that people do, and it's very common, I see it all the time, they'll take the 7.2% and they'll multiply it by this observed value up here. I'm not wanting 7.2% of the less than 5 to know what this whole group would be that are less than 5 years old. That doesn't even make sense. So it's going to be 7.2% times 455, and every one of these are going to be times 455. And here's what makes sense about it. This should add up to be 100%. And when I take 100% of 455, I should get about 455 actual individuals that I expect. And so these two numbers, the total of the expected and the total of the observed, should be a way for me to check myself, and those should be the same. So I'm going to take 455 and I'm going to multiply it times the decimal version of 7.2%. So times 0.072, and I get what looks to be an odd number. Like, it's a decimal. There's obviously no such thing as 0.76 5-year-old, but you would expect to have decimals because of what you're doing to calculate it. So it's another start. It's okay to have decimal values in your expected. Whoops, where my expected. So I usually go to 2 decimal places. There's no magic to any of it, but that's what the critical value would be from the table. So that's where I tend to stay. So I'm going to start again. I'm going to take 455 every single time, and I'm going to multiply that now by 0.136. Make it 61.88 people that I would expect to be in the age bracket of 5 to 14. Then I'll take 455 times 0.671, and I have a number. I'm going to go ahead and round it just because I'm going to go with 2 decimals. This is when I wish you were here, because y'all make sure I don't do stupid math things. And then I'm going to take 455 times the last percent, change it to a decimal, 0.21, and I get 55.06. Then you have a way to check to make sure that you've got your numbers right, because there's nothing worse than doing all of this work to find out later that the beginning was wrong. So a really important check is to take all of your expected values, and they should be about 455. So 32.76, 61.88, 305.31, 55.06, and I get 455.01. Super happy with that. So to show myself I did this, first of all I added it, I kept a record, and then I just tell myself I'm happy with that. And then everything else is exactly the same. So you'll take your observed values and subtract your expected, so you find the difference between observed and expected. Then you're going to square those differences. Then you're going to take the differences squared over expected. Now this is going to be where you realize that things are different, because you're going to be dividing by a different number instead of where all the expected values were the same before. Now they're different, and you're going to have these differences squared are going to be divided by this number, and then it'll change, it'll change, it'll change. Okay, so I've set this up for you. Let's go to the second one. So now we have people who are out observing deer, and they counted that there's 320, and they know what percent of the areas are covered in plants. So deers are herbivores. It would make sense that when you have more plants, you'd have more deer, because there's more resources there to support, and that's what they're going to check to see. So I think I'm going to do mine, because I want to add the null and other things. I think I'm going to do mine each on a separate page. So my categories are going to be the areas. So I'm going to go ahead and get this written down. So I have feeding area A, B, C, D, E. And then you do not put this directly in your table. The percents, you have to do the extra work to get your expected values from those, but you do put the observed value directly in your table. So observed, I've got 102, 125, 43, 27, 23. I can't put the expected in yet, but I am going to go ahead and write down the percentages of the plant composition. So 32, 38.7, 12%, 9.3, and 8%. And I'll show you what I've got. So I wrote down the data for the observed. So this is given to me. This is given. The expected, I have to calculate. So the first thing I'm going to do is I'm going to get my total of my observed. So I've got 102, 125, 43, 27, 23. I know they gave me the total, but I'm going to check, and it's 320. That's what they said that they had done. This is super important. So that's the number I'm going to use every single time. So I'm going to multiply each one of these percents times 320. Because then I should have 100% of 320, which is 320, as the total of my expected. So I'm going to take 320 times 32 as a decimal, 32% as a decimal, so 0.32, and I have 102. Again, a decimal's fine. I know there's no such thing as 0.4 deer. 320 times 0.387. And I get 123. Things are looking really good. Those values are very close. 320 times 0.12, 38.4. And 320 times 0.093, 29.76. And 320 times 0.08. And we have 25. My prediction, low chi-squared, and that the hypothesis that there's no difference between what I observed and what I expected, I think you'll accept it. That's just a guess. I think it's good to, as you're working, prepare yourself for the answer. So now let's do a check to make sure before we do math that we've got these correct. They should add up to about 320. So I've got 102.4, 123.84, 38.4, 29.76, and 25.6. What? One more time. 102.4, 123.84. Nope. 123.84. Okay, I quit. 102.4. 123.84. 38.4. This can't be that hard to punch buttons. I have days like that. Okay, wow, it's dead on. Even if it had been off a little bit, I would have been fine with it. You're going to do the exact same thing you always do. I'm going to take the observed minus the expected. Then I'm going to square those differences. And then I'm going to take this value of the differences squared, and I'm going to divide it each one by their own expected values. So you're going to have what you divide by will be different. And then again, you'll go through and you'll do the whole thing. And we'll talk about what you should include. You already know that, but I'll remind you. All right, last one. We're doing 3. Oops, here we go. So, Lake Lulu. I like that name. Fish and Game Department stocked Lake Lulu. That would have been a good name for Lily. Because have you ever heard somebody go, oh gosh, she's a Lulu. She is a Lulu. I like it. Oh well, she's Lily. They're going to stock it with fish, and they had certain proportions. Now, that's not accurate. Percents aren't proportions, but we're going to be okay with it. With the following distribution or percentages. 30% catfish, 15% bass, 40% bluegill, and 15% pike. Now, notice they didn't give me a data table or anything at all. So I'm going to move those data. I'm going to use another page. I'm going to look at this. I think I'm all a good third way through my notebook. I said, look at this, and then you couldn't see. But anyway, so I had catfish, bass, bluegill, pike. Pike are scary. 30%, 15%, 40%, and 15%. Okay? And then they said 5 years later, they go out in the lake, and they sample 500 fish in the lake. That's a lot of fish to sample. To see if the distribution, that's a better word, of fish had changed, as shown below. So way down here, they're telling you what they found. They didn't put it in a table. They just told you, here's what we caught. So I'm going to set that up. I've got catfish. And they observed, 120 bass, 85 bluegill. Ooh, bunch of bluegill. 220 and pike 75. Now I know they told me, point with my finger like you can see it, 500, but I'm still going to add my observed values. So I wrote all this up from the information in the question. So first thing I'm going to do is total my observed values. I would expect 500 because that's what they told me. I could add them in my head, but your head's a liar. Like, you need to not do things with your head. When you're taking a test, stress and anxiety cause you to only be able to really access about 70% of what you're capable of doing. It impairs you that much. So don't trust your head. Your head's a liar. So 120 plus 85 plus 220 plus 75. Sure enough, it is 500. That is the most important number on the page, because I'm going to use it to say, okay, so originally this is what they set up. So if they're the same, 30% of the 500 should still be catfish, 15% of the 500 should be bass, 40% should be bluegill, and 15% should be the minnow pike. So I'm going to take 500 times 30% as a decimal, 3, and I get 150. 500 times 0.15 for the number of bass I would expect, 75, 400. Now I can do that in my head and I know it's 200, but I'm not going to do it in my head because my head's a liar. So times 0.4, I get 200, and then 15% of 500, so 500 times 0.15, and you get 75. That looks good. Now these are a little off, but your sample size is pretty big and you have 4 categories. So if I had to guess, I would expect a fairly nice low chi-square, which means low differences between what you observed and you expected. So I'm going to add these up now and just do a check for myself. 150 plus 75 plus 200 plus 75, and I get 500, which that makes me happy. And at this point, you're going to do the same thing in the table. Expected was this I calculated. This was given to me. And so I'll take the differences. Oh, that became crazy. Squared. It's always observed minus expected. And then remember that you're going to divide by different numbers here. So I think what I'm going to do is I'm going to stop the video for a second, and I'm going to give you another question that you set up yourself and that I don't set up with you. And let's see how that goes. So let me hide that little bar from me. Okay, there it is. Okay, remember these guys? Hello, M&M's at 6-ish in the morning. So I don't know if you've already opened and eaten yours, but if you did, I hope you kept your data. If for some reason that you ate them and didn't keep your data, we do, oops, let me turn the page. We do have mine. So, alright, so many papers and I've learned it's super loud for you. I hate that. Okay, so here are my M&M's out of my pack. And we're going to actually do the work here. So you might want to, we might want to glue this in. So here's what I've learned. When it's one page, I either want to cut it and glue it one on each side, which is what I think I'm going to do. Or if you're going to fold it, make sure that you put these on the right side, because otherwise if you put them on the left, that tends to flop open. So I think I'm going to cut this one, and I'm going to glue it in. Okay. So you do want this in your notebook. So you've got your own work here. Okay. So here's the way this works. We're comparing this tiny little sample of M&Ms to what the company says for all of their M&Ms. So we're going to use these percentages and work the problem in the exact same way. So we'll put my data in, but I'm not going to do anything else with it. I'm going to come back, and why don't we just all use my data to begin with, and then you can do your own, and you'll have an example of one. So that way we can check it. So I have 2 brown. And do they have different, or they taste different based on their color? I've not ever felt like they did. Okay, so 2 orange, and I have 2, 4, 5 yellow. So we're all going to put my data in here, so we can come down here and check later and see if we have the same thing. Blue, I have 4. Oh, I'm noticing something. I have 3 green, and no red. So count how many total I have. Actually, I'm not going to do that. I'm going to leave you right like this. You have at it. And then I'll put this in Edpuzzle as a quiz, and you can see how you did. So I got to go work problems so I know the answers when I grade your stuff. And I'll include the answers at the end after you've already put your stuff in. So use my data and go through the steps, and I'll eat in while I work my problems. I'll be back with all of the answers. But by now, when this video comes back, you're going to have put your chi-square in, and don't forget, here are the things I want. So that's probably another thing I should tell you. So what you're going to do is, this is what you need to have. You need to have the null, so you need to write the null hypothesis. You need to do your math and give me your chi-square value. You need to write out your critical value. And you get that from right here. You're going to give me your p-value. You know what that is. There's only one we use. So I usually just mark out this one that I don't use. Get it out of the way. You're going to write your mathematical rule. And remember, in that case, you go first. Like, you go first. And then you write whether you accept or reject the null. Okay? All of those things should be on every single one of those problems that we've done. Okay? You're awesome. Write something. Forgot degrees of freedom. See, if y'all were here, you wouldn't let me do that mess. All right, let's check our answers. We had no idea how long that took. It took a long time because I've got a million other things that came in the middle of it. So it's funny to start this, and it looks like by magic I did all of this super quick. This is not super quick. So for the first question we had that had to do with age distribution based on percentages in the Canadian population, my chi-square is 11.79. If yours is a little close to that, you know, like anywhere like 11.69 to 11.89, it'll be fine. And here's what I wrote for my null. I try to put as much detail as possible into the null, just because the basic null is that there's no significant difference in what you observed and what you expected. But you need to be a little more precise than that. Like, it needs to reflect what's going on in this actual problem. So if you wrote that general one, you wouldn't get credit for it in May on the exam. So I wrote, there's no significant difference in what did I actually measure. Well, I counted people. And so the number of individuals in, and I did this in Red Lake. I didn't do this, but you know what I'm saying. And it was in different age categories. And then I'm comparing that to what? What was I expecting? Well, it's the age distribution of the Canadian population. And I could put, as measured by the number of individuals in each age category, which is kind of repetitious, but it doesn't really matter. I guess you're figuring out that we're not English people. Like, we do repeat ourselves. If it's something that needs to be said twice, we say it twice, and we don't really care. So all the details that I needed, here's my chi-square value of 11.79. I have 1, 2, 3, 4 categories. So my degrees of freedom are 3. So if I go look at my table, 3 degrees of freedom, p-value of 0.05, the number I need as my cutoff of what's going to be starting here, it's too big, your differences are too big, is 7.82. 11.79, when I write my rule, I go first, is larger than 7.82, so I'm going to reject the null. And so I need to write just a little summary about what that means so that I get a take-home message. It means that the people in that Red Lake village don't match up per age group with the Canadian population. They're not a good reflection of that. They're different. Okay, so go second one. So this one had to do with, are the deer, so based on the resources, do the deer go where the resources are plentiful in the same proportion? So what you're really seeing is more resources, more deer. Less resources, less deer, and it's proportional. So I got a really small chi-square, and I think I told you as I was working this, I didn't expect anything significant. So this means there's no significant difference because it's really little. There's no critical value this low. So even if I didn't have a table, I could go, yeah, that's just definitely due to chance. I could have the differences I have. So here's what I wrote for my null. There's no significant difference in what did I measure. Well, I went out in the field and I counted deer at different areas. So the number of deer observed, and notice how I keep writing number because I counted them, of deer observed in each area based on what did I want to compare it to. Well, I wanted to compare it to the amount of resources based on the number of plants in the area. So based on the number of plant resources in the area. So my chi-square is 1.1. The critical value, I had 5 areas, so degrees of freedom are 4. So 4 degrees of freedom, p-value 0.05, is 9.49. That's my cutoff value for differences being too big. I'm nowhere near that. So my rule is, I go first. 1.1 is less than the critical value of 9.49, so I'm going to accept the null. And I just wrote a little summary. The number of deer found in each area is proportional to how much resources there are. So the more resources, the more deer. The less resources, the less deer. And it fit. So you didn't have something weird like there's very little resources here, but gobs of deer. So that would have been where you would have had weird numbers, and it probably would have failed. Okay, so let's look at fish. I'll move this so I don't have to move my head. So I wrote my null. There's no significant difference in the number of types of fish because that's what I actually counted. And I just put based on distribution because that's what we did when we originally did it. And there's no difference in the number of types of fish than the original number of fish that were stocked in the lake, also based on a distribution, which is right here. So I did my math. I ended up with 9.33. There's 4 types of fish, so degrees of freedom are 3. So if I go here, 3 degrees of freedom, p-value of 0.05, your cutoff is 7.82. Well, that's bigger. So 9.33 for chi-square. Here's your cutoff value, your critical value. Anything over this means that your data would not fit. And I let people know that I used 3 degrees of freedom 0.05, so I'm 95% confident in this answer. And I write my rule, I go first. My value I calculated, 9.33 for the differences, they're too large compared to the cutoff for the differences, so I reject the null. Because the null says there's no difference. My data say that there is a difference. So I'm going to reject the null. And I guess the fish just don't look like the original distribution. You just have different amounts of fish. To me, it looks like that the big contributor is that you just don't have the same amount of catfish. Maybe over time they just weren't as good at competing. All right, so for the deliciousness, which I've eaten them all, by the way, one thing I will tell you that's a huge big deal, since your expected values are different, so it matters what you divide by, is be really careful if someone like me pre-populates your table for you. That does not mean I'm being nice, because your data came in a different order. So if you did these and just moved them straight over, you've associated the wrong value with the wrong color. So all of this would be wrong. So you have to be careful. In general, they're not ever nice enough to give you this. They're going to give you a blank table. And most of the time, the blank table, regardless of how many categories, has 4. And then if you use 2 of them or 3 of them, fine. But they have kind of a generic table that they give us. So if your answer is wrong, I bet you moved these straight over. So another thing I like to do, because I'm always going over here trying to, with my eye, to find the number I'm dividing by, I like to box in my expected before I start my math. Because then when I get over here and I'm trying to remember what I'm dividing by, it's obvious that this is where I'm going in the box. So I got, for my little group of M&Ms, 6.02 as my chi-square. My null, I wrote, was there's no significant difference in what did I count. I counted the number of each color of M&Ms in a snack bag. And what am I comparing that to? Well, the number that would be expected for each color based on the data given by M&M Company, which I think it's Mars Company, actually, that makes M&Ms. So 6.02, there's 1, 2, 3, 4, 5, 6 colors, so my degrees of freedom are 5. You're going to find that the more categories you get, the much more difficult it is to have significant differences, because your critical value gets larger. So that critical value, I've got to turn the pages right here. Degrees of freedom 5, p-value 0.05, so my cutoff for the differences is 11, and I'm under that. So I can accept that this is just due to chance. Even if red were my favorite, and I didn't get any, and I think, well, that's like awful. I want to go complain because they're my favorite. I don't have any way I can complain because statistically, this is just due to chance. Nobody's cheating me or taking my M&Ms and making sure I don't get the red ones because I love them. It's just due to chance. This is just normal distribution. It's fine. And you're not going to hit the exact values you expect. So I hope that went okay for you. And I'll see how you did when I go through and grade them. But this is, as far as the math, this is as hard as it gets. So now, since you did mine here, what I want for you to do, and I guess I'll make it an assignment, is for you to do this exact piece, and I'll put this in a Google Doc, and then you can, how am I going to do that? I'm trying to think, because you're going to want to write it. Maybe you can just upload a picture. I hate to ask you to do that because I know it's not always easy to get it from your phone. I'll figure it out. Whatever. Maybe I'll just make it into something where you type in your amount and you tell me. Or I don't know. Maybe I'll just assume you did it. That's the easiest thing. Go do it, and then I'm going to assume you did it because you're the best.